So this is a second problem on the organic chemistry in week 13 of chemistry 2. And we're talking about carbocation arrangement. So carbocation arrangement is a combination of understanding first stability of carbocation. And in terms of that, primary, secondary, tertiary carbocation, this is much more stable compared to even the secondary, and primary is the least stable. And the sec is a combination of first portion and then something what is called a hydride shift. So what that means is if you're looking at along this compound, if there is something, this CH bond, right? So this one can form the bonding with your neighbors. So this one can switch their bond. Okay, so if this is this one can move around, and then they can essentially. So the one thing that is I want to make it clear because there's so many notations. So the better way to say it here is so much clearer is let's say you have this carbocation here, and hydride shift is about those two electrons will be connected to this way. So you will have this whole thing, right? This is a hydrogen with two electrons are shifted. That's why it's called a hydride shift. And then you ended up getting the newer species. So you developed in the cation here, and then you are going to form the new bonding on the other side, right? So you are shifting this. So what used to be here, the carbocation here, this is a newer carbocation. Obviously, this thing happens to essentially, for example, make this secondary carbocation to the tertiary carbocation by simply sweeping this one through. And I think that this one is actually a good example to show essentially the addition and then how this the hydride shift change their position. So if you first look at it, so I think from the previous problem, it is the same kind of logistics. So dilute HCl means you are going to have a H plus and the Cl minus, right? So this one there is this pi bonding. So that's a source of the electrons. So those are two electrons in the double bond. We're trying to make a bond here, right? So by doing so, first thing is so we have a CH. Let me just write just to make sure that you have the better case. So you used to have a CH2, and then this just to make sure that the beginning is good to have a very careful about. So this is a number of hydrogen, right? So to be consistent, so this is where your C, you have a CH and H, and then you have a C, and then there are the carbon with 3 methyl group, right? So that's a CH3, CH3, CH3. So that's all the things that has been combined. And then what I want to say is, there are choices. If hydrogen is connected to here, there will be a carbocation, right? Let me actually undo this. So I want to make a copy. So this is essentially, I just got rid of my double bond. So if I can actually make a copy and paste the image. So I these are the images to two different scenarios. And then what I can do here is, so this on hydrogen, they form CH bond, right? Then from the double bond, and then one can attach to here, and one can attach to here. Right? Those are the two options coming from the originally where they used to be the double bond here. Right? So I'm talking about forming the bond here, forming the bond, and it has been discussed before. As a consequences, you develop cations here, you develop cations there. And this is what we call the secondary cation, that's a primary cation. Right? Which one is more stable? This one. So therefore, this is not being considered. Okay, so that's the right protonation, and then I'm going to just simply write it as this, like that, with a cation showing up. And then if you really want, I can. Okay, if you want to really show, this is a new attachment from this hydrogen forming here, and the rest of them was just shown as it is. Right? And then now, this is, having said that, this is a secondary carbocation, and then now you are seeing this opportunity. So let me move some portions around. Okay, so this is a one, and then now I'm going to show the other details, which is okay. So this is a there should be a hydrogen there, and then the cations, and then there used to be these other two hydrogens. So there are another hydrogens, and there's another hydrogen. So that's what I can understand here. And then what this is going to happen in this scenario is they are going to have this hydrogen to go. Okay, so this one is actually is not hydride shift. I think that the whole methyl can shift to do this. So in this case, you're looking at this bond is going to form to the neighboring carbons here. Okay, so as a consequence, what you're going to see here is you're going to say this is a CH3. And then that's a backbone like this. This is on hydrogen. And then I'm going to highlight the new methyl, which is coming from here. That's a CH3. And then this is now neutral. And then you all of a sudden that you are going to have this. Right? So if you're looking at this portion, this is more like there is a carbon with, this is a carbon, CH3, CH3. That's the tertiary carbon from the secondary carbon here. Okay, so instead of the carbocation arrangement, that's sometimes the hydride shift is very easy to be done, but sometimes methyl shift. This is essentially methyl shift, and that's also possible to make a change from secondary to the tertiary carbons here. Okay, so what's going on here? To summarize, let's make the long story short. So you have this compound, and this one is essentially forming a bond. It's not double bond. Forming a bond. This whole methyl anion to forming a bond here. So by doing so, you have a new bond, and then you are left with this, and that's a plus. And then this one is they actually put, instead of putting it here, just for easiness, they can form the new bonding in this side. So what the new methyl group that used to be here is now shown up here, and by doing so, the nature of carbocation was changed from secondary to tertiary carbon. Okay, cation. So that is what they call the methyl shift. Methyl shift. You can call the methide shift, because it's actually the one is we're talking about CH3 with a negative charges. Okay, so this is a methide, which is sometimes you just call it a methyl shift. It's just an understanding about the moving the electrons around to achieve the better stabilities. Okay, so this achieve the better stabilities. So that's the first step, is a protonation. The second step is a methyl shift. And then what do you have now? Now is just the third step is pretty simple, which is, okay, you have a chlorine, which is looking for the is a nucleophile, and looking has a electron-rich compound, and then they can form the bonding here. So therefore, you have the bonding looks like that, and then you have formed a new bonding in the chlorine here. Okay, so that's a new bonding formation in the third step. Okay, so that's why you are seeing this chlorine attached to this position. So it looks like this is an unusual, because what used to be the double bond, and then this double bond acquired a new methyl group, and that methyl group is coming from actually methyl shift, just like here, and they create a new third tertiary carbocation, and then finally the nucleophile of chloride ion will form the bond. The genetic answers can be found from the what is shown up in the provided in the school text, and then this is the same thing, that okay, so they form the carbocation, and the secondary carbocation to the tertiary carbocation, the methyl shift will happen, and then finally chloride ion form the bonding, so that you make the new carbon chloride bonding. So the whole thing is highlighted by the methyl shift.